Good evening from Bangladesh. I'm Hussain, former professor, Department of Chemistry, University of Dhaka, Bangladesh. We are discussing a series of lectures on AS and A-level chemistry. And this lecture, that is the 36th lecture, is on acid-base equilibria. If we remember that our 35th lecture was also on acid-base equilibria. And in that lecture, I discussed conjugate acid-base pairs, then pH scale of a solution, then ionic product of water, and the last slide was about a problem, how to calculate pH of a solution. And I start with that problem again. Well, problem was that we have to find out the pH of 0.05 molar solution of sodium hydroxide. There are many methods to do that. I took only two methods to show you how we can calculate this. Sodium hydroxide, as we know, is a strong alkali. That means a strong base, which is fully ionized in solution. So what is given? Given that hydroxyl ion concentration in the solution is 0.05 molar. And we are asked to calculate pH. What is pH then? I said earlier, minus logarithm of 10 base logarithm of hydrogen ion concentration. What about ionic product of water? We also discussed that, and this is what we represent, the ionic product of water, that is hydrogen ion concentration, hydroxyl ion concentration. So if we have hydrogen ion concentration, we have to find out, and we have hydroxyl ion concentration 0.05 molar, and therefore this product of these two should be 1.0 into 10 to the power minus 4 mole square dm minus 6. Okay, so we put these figures, and then we find out hydrogen ion concentration, that is 2.0 into 10 to the power minus 13 mole part dm3. Or we can say this is the hydrogen ion concentration of this. And if we now take the logarithm, minus logarithm of this hydrogen ion concentration, we get the pH. And therefore we get the pH of the said problem is 12.7. Similarly, we can take another path to find out this. And how do we do that? We know POH minus and pH, POH and pH, addition of these two gives us 14, that we know. And how it is? The pH scale, if you remember, that it is 0 to 14, and lower pH is acidic and higher pH is basic, and neutral solution has got a pH of 7. So if we POH and pH to get together, and then we get 14, equal to 14. So from there, pH is equal to 14 minus POH, this minus POH. So we can get the 14 minus 1.3, this minus POH. POH is equal to 1.3, therefore we get 12.7. So in both ways, we can find out the concentration of a base. If we know the base concentration, then we find out the pH. Okay, and next is acid dissociation constant. What is acid dissociation constant? We use equilibrium constant for ionization of a weak acid. Remember, I'm saying weak acid. So equilibrium constant, weak acid, let's say general formula weak acid is this, HA. So HA in aqueous, we have an equilibrium, hydrogen ion concentration, aqueous, and A minus. And what is A minus? Then A minus is the anion concentration. Okay. So according to this equilibrium concentration, the Kc, we now say Ka, that what is means that acid dissociation constant. The acid dissociation constant we can write like this. That is Ka is equal to hydrogen ion concentration and anion concentration, and then hydrogen weak acid aqueous solution, which is called acid dissolution constant. And if we know acid dissolution constant, and then we also can find out the pH of this given solution. Let's go to the next slide. So we are asked to calculate the hydrogen ion concentration of the pH of hydrogen concentration and the pH of 0.1 molar solution of propanoic acid. Propanoic acid is an weak acid, and is Ka. This is acid dissolution constant is given 1.3 to 10 to the power minus 5 mole per dm³. So this is how the propanoic acid is being ionized, and this is the equilibrium reaction of propanoic acid. This A minus is here. A minus means propanoate ion. That is what is propanoate ion. So in this problem, we have to take two assumptions. So there is weak acid must be having a pH below 6. We have to remember this. And then ionization product, a little of the propanoic acid ionizes in water. What do we know? We have to know that the weak acid we are talking about, the ionization should be less than 5%. These two assumptions, taking these two assumptions into account, we can find out the, we have dissociation constant, and then we get also concentration, and therefore we can find out this, calculate it, and find out that the pH of this propanoic acid was 3.4. 3.4. Okay. Next, we go to indicator acid-base titration. This acid-base titration is in your syllabus. And what do we need to have an acid-base titration in practical classes? What are the equipment we need? So you see that there are two possibilities. You can have an pH meter. Also, you could have an litmus paper to test whether a substance is acidic or alkaline. Well, then we also use indicators to acid-base titration. What is indicator then? The indicator is a dye or a mixture of dyes. What does it do? It changes color over a specific range of pH. In simple terms, many indicators can be considered as weak acid. So we know that weak acid's dissociation. So here is an acid, which is an indicator. Before dissociation, we can have hydrogen ion concentration and ion minus. So this is unionized indicator, and its color is A, let's say, and the conjugate base, which is color B. So when this dissociation constant, if we add an acid to this indicator, what happens then? If we add acid to this indicator, that the equilibrium constant or equilibrium shifted towards the left, but if we acid and alkali, then equilibrium shifted towards the right. Okay, here is an example of an indicator. We call it phenolphthalein. This is how, if we add acid, then we have this structure of phenolphthalein. You see, please do mark that we have an OH functional group here, OH functional group here. And then if we add alkali to it, see that we don't have an OH functional group here, just minor change in the structure. And therefore, this colorless solution become pinks when it is base, when it is an acidic condition, it is colorless. So this allows us to have acid-base titration and using a pH meter. So we can measure the pH and react acid with base or base with acid. and then choose a particular indicator and see the change of color, and then we can calculate quantitatively the amount of acid or base. Okay. We go to the next. Well, the indicators, their property, I say, that the pH range is in between 1 to 2 pH unit. All indicators which we use, that we will see that the pH range is between 1 to 2 units. So, for example, methyl violet, its color, when it is at lower pH, that is when it's acidic, we get yellow. When it is higher pH, that is in basic condition, it is blue. And the pH range is 0.0 to 1.6. So we get end point. That means when we take a acid and titrate to the base and neutralize it, at the point when it neutralizes, we call it end point. So at end point, it will be blue. We can see that it's getting blue now. Then this range of the pH, end point is 0.8, range of pH is 0 to 1.6. Similarly, we can take some of the indicator which we use in titrating acid base. So here are some indicator: methyl violet, methyl yellow, methyl orange, bromophenol blue, bromokessel green, methyl red, bromomethyl, phenolphthalein, and so one or two of these indicators we use at least in A level for acid base titration as an indicator. Next, well, here it is. Let us see. This one is a pH meter. So this one is a pH meter. What we are doing here, we are adding. This is a conical flask. We are adding hydrochloric acid from burette, and in the conical flask, it was sodium hydroxide. So here is a magnetic stir. We stir continuously, adding hydrochloric acid to it, and we will see that when pH is 7, almost 7, we get the end point from here. I have taken two graphs here with a specific reason. You see, here is a graph for titration of a base with acid. Here is also another graph, titration of a base with an acid. Okay, so here we use bromomethyl blue, and this is blue when the pH is higher than 8 or so. At 7, it changes color. So at this pH, we the end point. We reach the end point. The range of bromomethyl blue is given here, 7.6 to 7%. Okay, phenolphthalein. You see, if you remember, we were talking about phenolphthalein and said that it is colored when it is basic in condition and colorless in acidic condition. Therefore, here with the range, you see that it's 10.8.2 to 10.0. This is the indicator pH, and neutralization point is here. You see, but another graph here, it looks like this. You see? So what is our conclusion? Why this is so? What is our conclusion? And why this is so? They both are a strong acid and strong base. Why this is so? Remember, I said, what do you take in conical flask on what you are adding from burette? That is the reason. If you take hydrochloric acid in the conical flask and add sodium hydroxide from the burette, you get a graph like this. Why it is? Because if it is hydrochloric acid here and 0.1 molar hydrochloric acid, let's say, we will have a pH before we add alkali, we get a pH of 1. And when it is neutralizing point, we get this base and pH of almost 10 or 11. So when we, depending on the conical flask, the material in the conical flask, if it is base in conical flask, you see that you started with a pH, basic pH, and strong base. Therefore, you are starting with 30, and it comes out like this and go to an acidic position. Here we started with conical flask with acid, and then we go to like this and space. So this is the nature of the graph for strong acid and strong base. Do we have always strong acid and strong base? No, not at all. So we see the possible graph for the in the next slide. Yeah. We say that we are titrating a weak acid with a strong base. The graph is like this then, because a weak acid is around 3 or so. Pure ethanoic acid is a weak acid. Its pH is around 3, and then it goes like this. And then you see when it equivalence point, its pH is about 8.7, which is in base, ethanoid, sodium ethanoid. So this is a salt sodium ethanoid. We see a equilibrium reaction, ionization reaction of this weak acid, ethanoic acid. We come to the next, strong acid with a weak base. We have to see strong acid. We started with strong acid with a weak base, and then you see here the base, it's below 10. So it is a strong acid and weak base. So our aim is to remember what we are doing, what sort of acid we have taken, what sort of base we have taken, and what sort of indicator we are using to get the pH curve of this titration. Okay? This is both a weak acid and weak base. And you see, we start with the weak acid, and then we titrate it like this, and then we get a weak base. So weak acid, weak base shows like this. So these are the acid-base titration of acid-base equilibria, I should say there. So in practical class, you do get this to be done in practical and see the graph and record the pH and find out the graph of lines. Okay. Next, we have a buffer solution. What is buffer solution? That and why we are talking about buffer solution. This is another thing we have to discuss a little bit. The buffer solution is a mixture of molecules and ions in a solution. Okay. But the pH more or less constant. A buffer solution has pH more or less constant when we add little bit of acid or little bit of alkali, then we say that it is almost constant. Why you use this sort of solution? Well, you see, buffer solution helps to stabilize pH of blood in medicines, in shampoos, water in swimming pools, and many other solutions in living things and domestic products and in the environment. You see, here is an example of a patient who is using eye drops containing buffer solution. And why? But so it should not irritate the sensitive surface of the eye. And that's why we make the eye drops in buffer solution. Okay, buffers are also important living organism. What about a normal person's pH of blood? It ranges between 7.35 to 7.45. Chemists use, and very much buffers when they want to investigate chemical reaction at a fixed pH. And let's talk about a typical buffer. A typical buffer mixture consists of a solution of a weak acid and one of its salt. Example, but you can a mixture of ethanoic acid and sodium ethanoate. This will give us a buffer solution. It will have a particular pH. We have plenty of both buffer solutions in many of our I would say experimentations. How a buffer solution reacts ionizes. You see here it's a acid molecules, and we are adding water to it. What happens? We get a base ions. This is a conjugate base, and this is the conjugate acid of this. So that is the plenty of weak acid to supply more hydrogen ions in the alkali of is plenty of ions from the salt able to combine with hydrogen ion, and if acid is added to it, stays roughly the constant so that the pH hardly changes. That's what we had said already. So up to this, if we talk about acid-base equilibrium for 35th lecture and 36th lecture, we discussed almost the syllabus of acid-base equilibria of AS and A-level chemistry. Next, what we talk in the next lecture, we will start with transition metals. You know, I have been talking about periodic table, and if you look to the periodic table, and if you take 1 and 2 group, and then 13, 14, 15, 16 group, and in between these groups there are D blocks, and we will be talking only the first transition groups as it is in the syllabus of AS and A level, but this 3D level, 3D orbital containing elements. These are transition. Similarly, 4D, 5D, 6D, all are transition metals. We will talk about transition metal one by one, its properties, the electronic configuration, what are the oxidation states, etc. in our next lecture. Thank you very much for your attention. We will meet again in the next lecture. Thank you so much.